In the last video, I introduced some new terminology related to robotics. Links, joints, end effector, manipulator, workspace, and degrees of freedom. In this video, I'm going to talk a little bit more about degrees of freedom, and we're going to look at some examples to show how we could pick how many degrees of freedom we want our robot manipulator to have. We're going to see in this video that most robot manipulators have either 3 degrees of freedom or 6, and I'll show you some examples to indicate why that is. In order to help illustrate the concepts of degrees of freedom as it relates to Workspace, I'm going to build a little robot manipulator on my box here. A robot manipulator is just a series of links and joints. So for my example, I'm going to use some of my erector set pieces to build this manipulator. I'm going to use pieces like this for links, and I'm going to use these little plastic pieces for joints. So I'm going to start out by building a 1 degree of freedom robot manipulator on this box to show you what the workspace would be in this case. So here I have my very simplistic 1 degree of freedom manipulator. I can tell that it has only 1 degree of freedom because it has only one joint. And this joint is a revolute joint rather than a prismatic joint because it allows the joint to rotate rather than slide in a linear fashion. Now, in this manipulator, the end effector would be located right here at the end of the link. And what I want you to do is imagine in your head the space that this end effector traces out as I rotate this 1 degree of freedom manipulator throughout its entire 360 degree rotation. This space that the end effector traces out as I rotate the link is the manipulator's workspace. So in this case, the workspace of a 1 degree of freedom manipulator is a circle. In other words, the workspace is a one-dimensional space. Next, let's take a look at a 2 degree of freedom manipulator. So here I've built a 2 degree of freedom manipulator. You can tell it has 2 degrees of freedom because it has 2 joints. And once again, both of these joints are revolute joints. Now, there's more than one way that you can build a 2 degree of freedom manipulator. This one that I've built here is called a 2 degree of freedom planar manipulator. It's called a planar manipulator because the end effector, when I move these 2 joints, it always moves in a plane. In other words, the end effector always remains on the same surface. Now, what I want you to do is, as I move this manipulator around, try to imagine in your head the path that the end effector sweeps out and see if you can figure out what the workspace is for this 2 degree of freedom planar manipulator. The way you figure that out is by first holding the first joint steady and rotating only the second joint. And picture the path that the end effector sweeps out. In this case, the end effector sweeps out a circle if I successfully hold this first joint constant. Now, I'm going to imagine that circle that the second joint sweeps out moving around in the path that the first joint sweeps out. So I'll have this circle from the second joint moving around rotating around the first joint. And every space that this, or every location that this end effector can reach, is a part of the workspace for this manipulator. The workspace for this 2 degree of freedom planar manipulator will look like a disk. I'm going to show you a picture now to represent the workspace of both a 1 degree of freedom and a 2 degree of freedom manipulator. And what you'll notice is that while the 1 degree of freedom manipulator has a one-dimensional workspace, the 2 degree of freedom manipulator has a two-dimensional workspace. Here I've shown a picture of a 1 degree of freedom manipulator. It's a single link free to rotate about its centered joint. As it rotates, the end effector traces out a path that is a circle. This circle is a one-dimensional shape. In other words, it has length, but it does not have width or thickness. Here I've shown a picture of a 2 degree of freedom planar manipulator. The second link here is free to rotate about its joint, creating a circle. This entire circle is then free to rotate about the first joint, as so. So that the workspace of this manipulator is this entire area created by or bound by these two lines. This space is a two-dimensional area because it has both length and width, or radius and angle. So the workspace of a 1 degree of freedom manipulator is one dimension, a circle. And the workspace of a 2 degree of freedom manipulator is 2 dimensions, a disk. So now you might be able to predict why it is that many robot manipulators have 3 degrees of freedom. You would expect that a 3 degree of freedom would have a workspace that is 3-dimensional. Having a 3-dimensional workspace is very useful since space consists of 3 dimensions: length, height, and width. I'm going to now show you an example of a 3-dimensional manipulator. Here I've built a 3 degree of freedom manipulator. It has a joint right there, there, and a third one up here. This 3 degree of freedom manipulator allows rotation around its base like this. I've switched to more of an isometric view here so that you can see this a bit better. It can rotate about the base. It can rotate we call this the shoulder of the manipulator right there, and then we also have the elbow that can rotate here. If you imagine the space that the end effector of this manipulator traces out, you can see that this manipulator can reach points in a 3-dimensional volume rather than simply a 2-dimensional area as the 2 degree of freedom manipulator, or simply a line as in the 1 degree of freedom manipulator. You might recognize this design of manipulator from industrial equipment or even from your own arm, and there's a good reason for that. This is a useful manipulator design for being able to reach having a wide workspace. One final thing that I would like to point out in this video is that while it is true that it is required for us to have at least 3 degrees of freedom in our manipulator in order for the manipulator to have a 3-dimensional workspace, It is not true that every three-dimensional manipulator has a three-dimensional workspace. In order to show you an example of that, I've built here a manipulator that has 3 degrees of freedom, but its workspace is only two-dimensional. This is true because this is a 3 degree of freedom planar manipulator. All 3 of these joints in this manipulator have an axis of rotation that is parallel to the other ones. And so the end effector in this manipulator always moves in a plane. In order to build a 3 degree of freedom manipulator that has a 3-dimensional workspace, at least one of the joints has to have an axis of rotation that is perpendicular to the others. This kind of a manipulator that has more degrees of freedom than it has dimensions in its workspace has a particular term. It's called a kinematically redundant manipulator. A kinematically redundant manipulator is one that has more joints than are necessary, or more degrees of freedom than are necessary in order to achieve its dimensionality of workspace. So, a 2 degree of freedom manipulator that has only a 1-dimensional workspace would be kinematically redundant. Or, as shown in this case, a 3 degree of freedom manipulator that has a workspace that is only 2-dimensional is a kinematically redundant manipulator.